Hello friends, in this video I'd like to solve the following problem from the Nordic Mathematical Contest 1988, problem number 5. Let m sub n be the smallest value of the following function, f sub n of x equals the sum which goes from k equals 0 to 2n of x to the power of k. We wish to prove that the limit of m sub n equals 1/2. So in other words, we want to show that the limit of the minimum of next terms, next functions in our sequence, that this limit is 1/2. This problem is quite challenging in my opinion. I will give you some hints. First, show that for every positive integer n, this minimum is always greater than or equal 1/2 by considering separately cases where x are from -infinity to -1 or from 0 to +infinity, and consider separately cases where x is from -1 to 0, making the graph of the first few functions might be very useful. Next, this formula will be immensely beneficial. 1 plus q squared and so on plus q to the power k minus 1 equals 1 minus q to the power of k over 1 minus q is the formula for the sum of geometric progression. Once you have a lower bound for m sub n, to show that our limit is 1/2, try using the squeeze theorem. So in other words, try to find upper bound for m sub n, and that upper bound should also converge to 1/2. The really hard part is finding this particular bound, and my hint is try looking at f of n of x of n, where x of n I define as -1 plus 1 over square root of n. And also remember one fact from mathematical analysis, namely, if we have a sequence which goes to 0, then the limit of 1 plus un to the power 1 over un converges to Euler's constant, Euler's number, E. So give this problem a try and I will see you in a minute. Okay, so first of all, let's look at some graphs. Here I have prepared in advance graphs of first few functions, f1, f2, and so on. Maybe I will magnify it a little bit. Okay, and now let's notice the following. First thing which is obvious from the graph is that our functions attain their minimum somewhere between -1 and 0, somewhere from there to there. And from our graph we see that in fact these minimums seem to converge to 1/2. And moreover, from these graphs we see that for every function, or for every one of the first 6 functions in our sequence, from -infinity to -1 and from 0 to +infinity, values are always greater than or equal 1. So now we will wish to prove all of it formally. Okay. So I will proceed as follows. First of all, let's take our formula for fn sub of x, which is 1 plus x squared plus x cubed and so on, plus x to the power 2n minus 1 plus x to the power 2n. Okay, and now I will do the following. I will take one separately, and then from these two terms I will factor out x, and I will have 1 plus x. Maybe let's write another term right here. From these two terms I will factor out x cubed, and I will have 1 plus x as well, and so on. Finally, from these two terms I will factor out x to the power 2n minus 1, 1 plus x. And that I will put 1 plus x in front. And moreover, look closely. Here we have x, x cubed, x to the fifth, and so on. From every summand, I can factor out x as well. And I am left with 1 plus x squared plus x to the fourth power, and so on, plus x to the power 2n minus 2. Okay, very well. And then now we see the following. If x is either in this interval or in this interval, then fn of x is necessarily greater than or equal 1. Why is that? Well, because here we have only positive terms or non-negative terms, and this part is a quadratic function which happens to be non-negative exactly on this interval. So all of that is non-negative on this set, so our function is necessarily greater than or equal 1 in this case. Okay, so we now know that our minimum is probably not attained in this set. So now let's look at x's which are from -1 to 0. And I will do the following. I will take again my formula for my function. And now what I will do, I will apply the formula for the sum of geometric progression. It will be 1 minus x to the power 2n plus 1 over 1 minus x. Okay, and now let's notice something. First of all, this part right here, this is greater than 0. Why is it greater than 0? Well, because we are considering negative x's, and minus x to an odd power is a positive number. So necessarily this fraction is greater than 1 over 1 minus x. And moreover, since we are dealing with numbers from -1 to 0, the denominator will be greatest if our denominator is always less than 2, so the entire fraction is necessarily greater than 1/2. Okay, and that means that minimum over all real numbers of our function is necessarily greater than 1/2. Or in other words, m sub n is greater than 1/2 for every positive integer. Okay, so now we have one bound. Now the really hard part is finding the other bound from above. And to do that, I will consider, so I will write once again that fn of x, I have derived this formula, and I will consider plugging x sub n, which I define in the following way: -1 plus 1 over square root of n. Why this sequence? Well, one hint is looking again at the graph. You can see that the arguments at which the minimum is attained seem to be moving to the left, seem to be converging to -1. So probably it might be helpful, it might be beneficial to consider some type of sequence which goes to -1 from the right side. This sequence goes to -1 from the right side. But why square root of n and not just n, for example. You will see in a minute. And now, obviously, m sub n, which is defined as the minimum over real numbers, is necessarily less than or equal this number. Why is that? Well, because on the left hand side we have minimum over all numbers, and on the right hand side we have f of n at one particular argument. And now let's plug in. So we have, I will plug into this formula which I mark asterisk. Well, we have the following: 1 minus 1 plus 1 over square root of n to the power 2n plus 1 over 1 minus 1 plus the square root of n. Very well. And now let's simplify it a little bit, or transform it. First of all, in the denominator, I will have 2 minus 1 over square root of n. In the numerator, and because my exponent is odd, I can write everything in this form: 1 plus 1 minus this to the power 2n plus 1. And now the part which we expect, or we are hoping that this function will go to 1/2. This sequence will go to 1/2. How to check it? Well, let's take this sequence once again, and I will do in a minute one trick. Let's put it lower. Let's put everything lower. Perfect. And now I will do the following, because look what's happening. This part will go to 0 as n goes to infinity. This part is tricky because we have, naively, we will have 1 to the power infinity. We know that it's a problematic symbol. So we will make the following manipulations. I will write 1 minus square root of n, and here I will raise this fraction to the power minus square root of n, and moreover, I will raise this entire thing to the power minus 2n plus 1 over the square root of n. It works. It's exactly the same as the exponent which we had previously. Okay, and now, by the well-known theorem about convergence to the number e, this part in violet parentheses, this entire thing goes to e. And this exponent, it's pretty easy to see that it will go to minus infinity. Again, this goes to 0. So we have e to the power minus infinity, but e to the power minus infinity, it's just 0. So we have 1 plus 0 over 2 minus 0, which is 1/2. Exactly what we wanted. And now, once again, why I have chosen this sequence? Well, why not something simpler? For example, minus 1 plus 1 over n. If I had chosen minus 1 plus 1 over n, after plugging in our formula, you will see that this limit would not be 1/2. It would be something different, and it would say nothing. Okay, and now we are at the beginning, at the end rather, because now we know that m of n is greater than 1/2, it's less than or equal this. Moreover, we have established that limit as n goes to infinity of this thing is 1/2. So by the squeeze theorem, we know that the limit as n goes to infinity of m sub n is in fact 1/2, which is what we wanted, QED. Okay, so as you have seen, quite challenging problem, at least in my opinion. And yes, so in finding limits, the squeeze theorem and looking at the graph can be beneficial. That's my message for you. So thank you for watching, and I will see you in the future. Goodbye.